Okay, so let's get back at things with look at some torsion. So previously we'd been talking about equilibrium, axial strain stress, indeterminate axial load, so on and so forth. Now we're going to look at torsion and basically how to solve indeterminate problems that involve twisting. So in general, kind of the way the torsion causes deformation is you're going to get a certain angle of twist after you apply the torque to it. So any lines kind of drawn along the length of the object get twisted. Um, these radial lines, they stay straight, but they rotate. So it'll move from here to here. The circles at any cross section stays circular. This is for a circular shaft. That's not going to be if you have a non-circular shaft, the assumption that the cross section stays the same is not valid. But anyways, so as we uh, as we twist here, we get basically a certain kind of angle, well, between for the lines on the top here, which means that the angle of twist that we get, kind of like the how much rotation we get from here to here, um, increases as you move away from the x origin. So as you move down the shaft, the total angle changes and increases. If we're looking at the shear that's occurring, essentially, as we look at the cross section, so the shear increases linearly with the distance from the center here. So here, for some reason, the notation that they have a tendency to use when we're talking torsion problems, they use c as the outermost radius. They use rho here as the distance from the center for any generic point. Anyways, obviously, anyways, so at the center, when we're at the centroid, there's no strain going on because that's the point about which everything's rotating, and then you get more and more strain as you move away from the center, increasing linearly. So we get the strain at any point is equal to the maximum strain times the ratio of the point we're looking at and the maximum radius. So if strain's going to vary linearly, I think you can tell me what else does. It follows Hooke's law, so the shear stress is going to vary linearly as well. So if we look at any particular point here, if we examine a little cube of area there, that that cube's going to have a particular shear stress. That shear stress is going to be there's going to be a certain maximum shear stress at the outside because the strain's the maximum. Inside it'll be less. It'll vary linearly down here. And as a result of that, we can also tell that we can also figure out what's going on with the torque. So basically, if we have the stress varying linearly as it increases outwards, then that means that we have the force on that little bit of cube, on those little cubes, very linear as well. So what we can do is we can figure out, and we for each of those little cubes of force, they got a certain amount of shear stress, and that shear stress is acting perpendicular to the vector from the center to the point we're looking at. So it is causing a moment about the centroid. So we can figure out the total moment that's caused, aka the torque, by kind of adding up all those little bits of force. So the the moment arm here is the rho, that's the distance, and then the force is just the shear stress times the size of that little cube that we're looking at. So again, the shear stress can be put in terms of the shear stress max times this ratio. So again, we can those are all if these are constants, they can be moved to the outside of the integral, which leaves us the torque being tau max divided by c times this integral here. And then we can solve for tau max, and that'll be the torque times c divided by this integral here, and we're gonna call that J. That is what we call the polar moment of inertia for the cross section in question. And it's a function of the geometry of the cross section. So it's basically the torque equivalent of the cross section area. When we want to calculate the stress that the stress that occurs due to an axial load, it's equal to the load divided by the area. Well, okay, so when the J can kind of be figured, can kind of be looked at as the the A equivalent of that for torque. So we can figure out what that is for a circle, at least. It's fairly easy. So we just need to take this equation here, integrate it over the entire area. So okay, just start at the center, go out to the outside, and then so we got this distance here, and we got this area here. So the area, the little differential area that we're going to be looking at, that's just going to be the circumference of that circle times the thickness of that little line there, which that'll be a differential in terms of the distance there. So dp or d rho, that's not a p, it's a rho. So again, you can just move the 2 pi out to the outside. We get rho to the third d rho integrated. That gives us 1 over 2 pi c to the fourth for a circular cross section. So yeah, and just always keep in mind that our shear stress varies linearly from the outside to the maximum at some point. It's a function of the distance from the centroid. Oops, went too far. So based upon that, we can figure out what sort of angle of twist we have. So we know that we have a certain amount of shear stress that we're being induced. That's based upon that here. And we also know that if we look at this little cube here, and we apply shear stress to it, we apply some sort of shear stress to this face, it is going to cause a certain amount of strain. And the amount of strain it's going to be, the relationship between the amount of strain and the stress induced is going to be a function, a function of Hooke's law. So we can figure out that relationship there is based upon, I'm trying to select this, erase that. Yeah, so based upon our shear modulus. So we can kind of rejig this to give us our tau max in terms of the G times the maximum shear strain. And then if we know that shear strain, we know that basically it's going to cause a certain amount of displacement going on here. So I'm going to call that d theta. So at the outside of at the very outside of our cross-sectional area, d theta is going to be our gamma max times the width of this little differential slice we're looking at. We're looking at a differential slice here. So we can so basically over that tiny little area, we're going to get a certain amount of relative twist. That'll be based upon, we'll call that the d phi here. So d phi is going to be basically a function of our d theta divided by rho. So we can solve for d theta in terms of the gamma max dx. And then we know what our gamma max is in terms of, all right, we know what our gamma max is in terms of stress. So basically we can solve for gamma max by dividing out the G, the shear modulus, to give us this. So we got our d theta over our d phi over dx is equal to the torque times the radius here divided by the j over the area and our g. So simple enough. We can just we got that expression here. Some of these will vary with the x position. So you know that the torque can change over the length of the object. The J can change over the length of the object. That's if the cross section changes. The G can change over the length of the object. You tend not to see that too often, but you know, if you have varying material properties, that could occur as well. I think probably the main situation where that might occur is if you have, say, a bar that or a rod that you're twisted, you know, it has a torque applied to it and it's being heated in a non-uniform manner. Then say you get based upon the temperature relationship, you could have different stiffnesses there, because obviously the stiffness of your material is a function of the temperature as well. You know, metals soften up and become more pliable as you heat them, hence the fact you can forge them into stuff. So anyways, yeah, so essentially in order to figure out what our total twist is, we just integrate that. So if we are assuming that we have a constant J and a constant G and a constant T over the length, then this is what our formula ends up being for the total amount of twist, the angle of twist over that length, relative from here to here. So the sign convention we're going to be using is fairly important. We need to keep our sign conventions in mind. Essentially, if you mount it on this end and have that as the x origin, any rotation about this x-axis that would follow the right-hand rule at the end is going to be a positive. So that's a positive twist. So it's a positive twist if it's applied to the far end of the x-axis, or it is a positive twist if you're sorry, it's a positive twist if it's applied to the far end of your x-axis. So it's also a positive internal tensile load if it's applied to the far end of your x-axis. Or conversely, if you if you have a if you have it rotating, if you have it applied the other way to the kind of near end of the x-axis, so closer to our origin, then that's also going to cause a positive twist and a positive overall torsional. So again, twisting. So yeah, so if we start with this, applying a torque like this is going to cause our our lines on the top to twist like this. It's the same deal as here. If we fix this end and apply this torque, that's going to cause that line to twist like that. So again, same angle, same sign of the angle here between the two. They're slanted in the same direction based upon that. So we'll do a quick example here. So we've got a bar rod that has different torques applied to it at different segments. So essentially, the way you would go about figuring out what sort of twist you have between one end of the rod to the other end of the rod is by figuring out what sort of twist you have from here to here, what sort of twist you have from here to here, and then what sort of twist you have from here to here, and adding it all up. Just keeping your sign conventions in mind. Well, you do that. So if we have a situation like this, then basically we can break it up into the different segments and figure out what sort of internal torque those segments have. So, for example, the first segment that we have here, in order to keep this thing in equilibrium after we take a section cut, we're going to have to apply a moment like that, which is going to be a positive moment, because again, we got our thumb in the direction of our x-axis here. I guess, oh yeah, I did define direction. This is the direction of the x-axis. So if our thumb's in the direction of the x-axis, and we're using our right hand, and our fingers curl around in the direction that the torque we're applying is, then that means that this is positive. Then we take another section take another section right here, and then essentially, in order to keep this in equilibrium, we're going to have to apply a torque around this way. So we apply that torque, and then our thumb's suddenly not pointed in the x-axis, it's pointed in the negative x direction. So it's going to be a negative 7. So the torque there, the magnitude of the torque there is going to be negative because of that. And then again, same deal on the other end. So if we apply a if we take a section cut right here, then we're going to have to apply a 10 kilonewton meter torque in order to keep this thing in equilibrium. And that'll mean that, and again, needs to be in this direction, so our thumb's pointed in the opposite of the x direction, so that's a negative internal force. So another way to look at it is if we're starting from left and going to right, if we're starting from the origin, the x origin, and moving in the away, then as we're applying, as we come across these torques that we're applying, these torque loads, then we can see how our torque graph changes. So for example, the first one that we hit here, is a uh, uh, looking at this one, the first one that we hit, that is going to be a negative. The first one there is a negative 80 kilonewton meter torque. So essentially, if you're moving from left to right, you kind of got to work backwards. So if you hit a negative one, then that means that essentially for a section to the left, for a section to the right of there, you've got that negative acting here instead of on this end. So hitting a negative one causes it to increase. So we can kind of go across and see that. So going from here to here, first thing we do is when we hit the origin is we hit a negative moment. So that increases our moment to 80. And then we keep going until we hit this positive moment. And that'll drop us down 180. So from 80 to minus 70. And then move across here. And then we hit the 60 kilonewton one. Again, that's a negative 60 kilonewtons based upon our right-hand rule. So that'll bump us up 60 kilonewtons to minus 10. And then at the very end, we hit our 10 kilonewton meter torque at the end, and that bumps us back up to 0. So from the start to the end, we should always get back. We should start at 0 and get back to 0 at the very end, including just including these jumps, including this line and including this line. We need to go back up. We need to start at and get back up to 0. So got those segments there. So we just need to in order to figure out the twist from here to here, we just need to add up these values here. So I'm going to go over to OneNote here. Okay, so we have our we know we need to add up the sum of our twists. So again, our twists given by the torque times the length. Torque times the length divided by jg. J in this case, pi over 2 times the radius to the fourth. So pi over 2 times 100 millimeters to the fourth, because it was 200 millimeter diameter shaft. So that gives us 157 times 10 to the 6 millimeters to the fourth. Our G is going to be 75 gigapascals, which I'm going to put here as 75,000 megapascals, because a megapascal is a Newton per millimeter squared. So keeping things in millimeters instead of working in meters, blah, blah, blah. So figuring out the the twist from one end to the other is just the twist of the segments. So AD is going to be the sum of AB plus BC plus CD. So again, we had from A to B, we had the positive 80 kilonewton meters. And here again, I'm just kind of going to be throwing in conversion factors. So 1,000 newtons per kilonewton and 1,000 millimeters per millimeter. And it was a 3-meter section there. So 3,000 millimeters. And that would just be divided by JG, but the JG is the same for all these sections. So what I'm going to do is I'm just going to add the terms on the top and then divide everything by JG once to save a bit of calculation. So we got that 80 kilonewton meters times the 300 millimeter, sorry, the 3,000 millimeters minus the 70 kilonewton meters times 1,000, blah, 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 times 2,000 millimeters. It was a 2-meter section, and then a minus 10. So minus 70 minus 10, and then I added the thousands, and already did this calculation, and the 15,000. The 1,500 millimeters is a 1.5 meter section there. And then all that divided by our J and our G. So that'll give us 8.5 times 10 to the 10 newton millimeters divided by 1.1775 times 10 to the 13 newton millimeters, which gives us this ratio. It'll be radians. So 7.22 times 10 to the 3 radians. 7.22 times 10 to the 3, 10 to the negative 3. So if you want that in terms of degrees, we're looking at 0.41 degrees. So again, I'd like to emphasize here that some of those twists will be canceled out. So most that positive twisting overall, all the positive twisting happens in this 80 kilonewton meter section, and then some of that twist gets reverted after the fact in the other sections. So yeah.